Can I ask a doubt about the platinum PTCl42 minus?
Sure.
Sir, is there a possible axis perpendicular to that plane passing through the platinum atom?
Yes, that is C4 axis. I'll show you that. This is the C4 axis. Okay. This axis, this is the plane of the molecule. This is perpendicular to that. This is perpendicular to that. This is the perpendicular axis. This is the plane of the molecule. This is the plane of the molecule. This is perpendicular to that. That's why I held this molecule like this. Or I can, if I hold it like this, it will be like this. But the plane of the molecule is this, and this is perpendicular to that.
Sir, what about I rotate that 180 degree? Is it?
Yeah, that's what I said. This is what is that? The C4. Then this is also same as the C2. Okay. Now suppose this is 1, 2, 3. I can rotate it through 90 degree. I get this. This is a symmetry operation. I can rotate it through what? 180 degree also. That is 180. So the C4 is the same as the C2. Do you get it?
Okay, sir. Both are coincidence.
Yeah, that's an excellent question. Thank you for prompting me to show it with the model here. See, any other question?
Dear participants, faculties, and students, do you have any questions regarding what sir has discussed?
May I know the name of the person who was answering to my questions? What's the name, ma'am?
Dr. Nitya, sir, from Tamil Nadu, sir.
From which college?
From Muthayamal College, Rasipuram, sir, in Namakkal.
Yes, I'm glad to meet you.
Okay. Yeah. Thank you, sir. Thank you so much, sir.
So this is a presentation 2, symmetry element and symmetry operation part 2. Mirror plane sigma, the inversion center. The contents, the mirror plane and inversion center. Be patient and study group theory. Mirror plane or the plane of symmetry. A mirror plane, this is quite simple, is an imaginary plane which divides a molecule into two equal halves, such that one half is the exact mirror image of the other. Let me show you. A mirror plane is designated by the symbol sigma. Now, let me label the two hydrogen atoms as 1 and the 2. Suppose I reflect this in a plane perpendicular to the plane of the molecule and bisecting the hydrogen, oxygen, hydrogen. So this plane passes through the oxygen atom, bisects the hydrogen, oxygen, hydrogen bond angle. I will show it in a model. So this is a water molecule. I hold it like this because both are in the plane. So this is a plane. Now these two hydrogen atoms will be interchanged. So I will get this configuration. The one will come here and the two will come here. So this is these two configurations are distinguishable or indistinguishable. They are indistinguishable configurations. So this is a symmetry operation. So a mirror plane is an imaginary plane which divides a molecule into two equal halves, such that one half is an exact mirror image of the other. The mirror planes may be classified into 3 types. Before we consider the classification of mirror planes, let us consider some very important generalizations about 1. The coordinate system to be followed. We're discussing the molecular symmetry and the 3 mutually perpendicular planes in this coordinate system. And these discussions are generally not carried out in the classrooms. That's the reason why the identification of the 3 types of the planes in molecule becomes such a tedious and difficult task. But once you know this important generalization, you will find it extremely easy to find out the various mirror planes in any molecule. For this, I'm not going to use any rocket science. I'm going to use only those concepts which you have studied in the lower class, in the school level. So, the important generalization about one, the coordinate system to be followed while discussing the molecular symmetry. Then the three mutually perpendicular planes in this coordinate system. Now look at this diagram. This is the photograph of a corner of a room. You can look at the corner of the room where you are sitting. These are the two walls. This is the floor. This is one coordinate. This is second. This is third. This is X. Then I take this as a Y coordinate. This is Z coordinate. And this is a three-dimensional representation of a three-dimensional figure. So you can very easily visualize the three mutually perpendicular axes, X, Y, and Z. But the problem we have is we have to represent this three-dimensional figure in a two-dimensional figure. This we do like this. Here, see, this is an X-axis. This is, of course, the Y-axis. This is an Z-axis. Sorry, this is Z, this is the Y-axis. So this Y-axis actually the perpendicular to the plane. But when I represent this three-dimensional figure, in this I have to make a components here. So here, which are the two axes in the plane of the paper and the plane of the screen? You tell me, which are the two axes which are in the plane of the screen?
Z and X.
Z and X. And this coordinate system is the Cartesian coordinate system. Here, the X and Z axis are in the plane of the screen of the paper, and the Y axis is perpendicular to the plane. You can visualize the Y axis jutting out of the paper or the plane of the paper. It's not very difficult to visualize that. So this will be, this is represented like this. Now, the choice of the axis. This is a Cartesian coordinate system. While assigning the proper rotation axis, we align a molecule in a Cartesian coordinate system in such a way that the center of gravity coincides with the origin of the Cartesian coordinate system. So we keep the center of gravity at the origin. The Z axis is selected on the basis of the following rules. One, if the molecule has only one proper rotation axis, that axis is chosen as Z axis. We discussed several molecules with a proper rotation axis. The C2, C3, C4, C5, C6. And there was one molecule which has only one proper rotation axis. What is that? There is only one molecule with only one proper rotation axis. What is it?
Water.
Water. You are exactly correct. Very good. See, the water. So, so this is an example. So this axis, C2 axis is taken as an Z axis. Okay. Now, so this is the first rule. The Z axis selected on the basis of the following rule. It's a logic, common sense rule. If the molecule has only one proper rotation axis, then that axis is chosen as Z axis. Then if the molecule has more than one proper rotation axis, the one with the higher order is chosen as Z axis. Can you think of example? I have given several examples. What are the various examples?
BF3.
Yeah, BF3, PTCl4.
L4 2 minus benzene.
And I can choose any of these examples. But can you guess which example I might have taken? This is, say, I have taken the PTCl4 has one C4 axis and four C2 axis. This is just the continuation of what you have already seen here, nothing new here. So that's why I said the more you learn, easier it gets here. So this is C4 axis, which is taken as a Z axis. The higher, then there are C4 and the C2. The higher C4 axis is taken as a Z axis. If the molecule has more than one higher order axis of the same order, then the axis passing through the maximum number of atoms is a Z axis. Read that once again. So this is the ethylene molecule. Okay, this is the ethylene molecule. This is an ethylene molecule in this ethylene molecule. This is one axis. Okay, symmetric axis. And what is the order of this? This is C2 axis, right? Then this is another C2 axis. It can rotate like this. Then there is yet another axis. This is a third C2 axis. So in the ethylene molecule, there are three C2 axes. This is one, then this is a second, this is a third. And these three C2 axes are represented in this diagram. Then there are three mutually perpendicular axes. You decide the Z axis according to this rule. Can anyone tell me?
The one which passes through the two carbon.
Yes, you are correct. If the more than one. So you must be able to apply what is in a statement to the real situation. You are not, mugging up this. You just apply this. Use your common sense. Then logically, so this is C2. So in ethylene, there are three mutually perpendicular C2 axes. And the C2 axis passing through the two carbon is chosen as that. Because these statements I have not taken from any textbook. I just interpret this rule. If the molecule has more than, then I look at this, then I say that in ethylene, there are three mutually perpendicular axes, and the C2 axis passing through the two carbon atoms is chosen as the Z axis. And even though the choice of the Z axis is generally unambiguous, the assignment of the X and Y coordinates are often arbitrary. Now the mutually perpendicular planes in a Cartesian coordinate system. See, again, a Cartesian coordinate is a line. So this is one dimensional. So it will be represented by a single letter. S coordinate, Y coordinate, and Z coordinate. But the planes are two-dimensional figures. So they should be represented by what? The two letters XZ, XY, XZ, and YZ. So the XY, XZ, and YZ are the three mutually perpendicular planes in a Cartesian coordinate system. So we start with X, XY, XZ, then YZ. Now, this is S coordinate. This is Y coordinate. I'm not going to, show this and request you to learn this. You are going to deduce this. Just one thing. The XY coordinate or XY plane will contain X and the Y coordinate. The XY plane will contain XY, X and Y coordinate. Can you identify the XY plane here? Which is this or this or this? Which is the XY plane?
First one.
This is 1. This is 2. This is 3. Which is?
3.
The 3. This is the XY plane. And what about the XZ plane? Of these two, which is XZ? This or this?
The second one.
Yeah, this is an XZ. What about this? This is XY plane. Okay? So in the 3 dimension, you can very easily identify the 3 mutually perpendicular. You can try it with the corner walls and the floor in the room where you are sitting later. Now, in order to understand and appreciate group theory, it is very important to know how to visualize and represent these planes in 2 dimensions. In 3 dimensions, that's perfectly all right. You have absolutely no difficulty. But when you come to represent these planes in the 2 dimensions, all the difficulties that come in. So, in order to understand and appreciate the group theory, it is very important to know how to visualize and represent these planes in 2 dimensions. These are the things which are not discussed in any standard textbook. Then representations of the XY, XZ, and YZ plane. The Cartesian coordinate, then X and Z axis are in the plane, and Y axis perpendicular to them. I'll just give you a direction. To draw the XY plane, Write down the x and y axis with reference to the Cartesian coordinate and complete the parallelogram. You try it yourself before I do it. You write down the x and y axis with reference to this Cartesian coordinate. Then complete the parallelogram. Has anyone completed that? Okay. So this is x and y. Then I complete it. So this is the xy plane. Similarly, we can draw the xz and yz planes also. Now you write the xz and yz plane. Draw the xz and yz plane. This is x and z. Complete that. This is xz plane. Then this will be the yz plane. So this is how you represent the mutually perpendicular planes in the two dimension. Now, if the coordinates are changed, the planes change accordingly. The x and z axis are interchanged. What was formerly z is now x. What was formerly x is now z. These two coordinates have been interchanged. Now you draw the xy plane. You draw the xy plane for this Cartesian coordinate system. You draw the xy plane for this Cartesian coordinate system. Xy plane for this Cartesian coordinate system. This is xy, this is xy. Then the xz plane. This is xz, this is the yz. You don't remember any of these diagrams. The only thing you will be remembering that you draw the axis with reference to the Cartesian coordinate system, then complete the parallelogram. Then depending on the situation, you can write your own the planes. A few important notes. It is not possible to have a fixed coordinate system while dealing with the symmetry of the molecule. We can't have a fixed coordinate system. The coordinates will change with the geometry of the molecules. So, always remember the general principle involved in the visualization representation of various axes and planes. So, it's not possible to have a fixed coordinate system. Always remember the general principle involved in the visualization representation of various axes and planes. The ability to visualize, represent the various axes and the planes is an important skill which is required by all students and teachers of the group theory. Unless the teacher or student is able to visualize and represent the various axes and the planes in the molecule, they won't be able to understand and appreciate the group theory. Now, classification of the mirror planes. The mirror planes are classified as vertical planes. Then vertical plane sigma b, horizontal plane sigma h, and the dihedral plane sigma d. A vertical plane sigma v contains the principal axis of symmetry. A horizontal plane sigma h is perpendicular to the principal axis of symmetry. A dihedral plane sigma d bisects the angle between two C2 axes. We have come across this situation. Say, in the C3, here, the boron trifluorine molecule, this is a BF3 molecule, this is a C3. And in the discussion of the C3 axis with reference to the boron trifluoride, I said, the C3 axis is perpendicular to the plane of the molecule. Okay, C3 axis is perpendicular to the plane of the molecule. Then I can make the same statement differently. I can say that the C3 axis is perpendicular to the plane. Or I can say the plane of the molecule is perpendicular to the the C3 axis. Okay? The plane of the molecule is perpendicular to C2. Say a horizontal plane is perpendicular to the principal axis. So the molecular plane is perpendicular to the principal axis. So this is the horizontal plane. Then a vertical plane contains the principal axis. See, this is one plane, C2 axis. This is second, this. They are present in the molecular plane. Our vertical plane contains C2. So you can say the axis is in the plane. Or I can say that the vertical plane contains the principal axis. So this is a sigma V. Sorry. This is a sigma V plane. This is a sigma V plane. This is a sigma V plane. Whereas the molecular plane is this. This is perpendicular to what? The C2, the C3 axis. So a vertical plane sigma V contains the principal axis of symmetry. A horizontal plane sigma H is perpendicular to the principal axis. Dihedral plane bisects the angle between two C2 axes. Now we shall identify the sigma V, sigma H planes in a molecule. You fix the Z axis, which is the principal axis first, and identify the three mutually perpendicular planes, XY, XZ, and YZ. Now, look at this. It's quite interesting. Of the three planes, XY, XZ, and YZ, the ones which contain the letter Z, the Z axis, or what? Of the three planes, the ones which contain the Z axis are what? XZ and YZ. So the XZ and YZ planes are the vertical plane because these two planes contain the Z axis. The XY plane, which does not contain the Z axis, is perpendicular to the Z axis. So the XY plane is a horizontal plane. So in this Cartesian coordinate system, the XY plane is a horizontal plane and the XZ and the YZ planes are the vertical planes. In a molecule, there can be more than one vertical planes, but never more than one horizontal plane. For example, in the BF3 molecule, there is one horizontal plane, but there are three vertical planes. And in the PtCl4 2- ion, there's one one horizontal plane, the molecular plane, but there are four the vertical planes. To sum up, the XZ and the YZ planes are the vertical planes. XY plane is the horizontal plane. Now, you label this plane. What is this plane? Anybody can answer this question. What is this plane? This is sigma XZ. So this is vertical plane. Then what about this plane? What is this plane?
That's also a vertical plane because it contains Z.
Yeah, what is the plane? Sigma?
Why is it?
Yeah, this is vertical plane. Then this is the XY plane with reference to that. So this is what? Perpendicular Z axis. So this is a horizontal plane. Okay. So these three diagrams will bring out the difference between what? The horizontal plane and the vertical plane. The horizontal plane is perpendicular to the principal axis, whereas the vertical planes contain this. You can see that the Z axis is in the plane. Z axis is in the plane, whereas this is perpendicular to the plane of the molecule. Then I change the coordinate, and this will be XZ, and then YZ will be this. That will be sigma V double prime, and the sigma, the XY will be like this. There is X and Y. This is, you draw this diagram, this is XY. So you learn one thing, you apply it to all similar situations. Now, mirror planes in some common molecules. Say, water is a plane on this. See, I will show this model. This is one plane, okay? Then this is second plane. Then if I consider this plane, this is not a symmetry operation because it will come like this. So this is not a symmetry operation. There are two. The plane. This is one plane, which is the molecular plane. And this is what? This bisects. So this is in the plane of the molecule. This is perpendicular to the plane of the molecule, but both are what? The vertical planes, because both will contain the C2 axis. So this is what there are two vertical planes, sigma, x, z. So with reference to x, y, z, this is x, this is z. So this is sigma x, z, sigma v prime, which is the molecular plane. Then this is z, this is y, this is sigma, y is sigma. You try to put these things in your memory. How the sigma x, z plane or the sigma x, z plane is a molecular plane. Sigma y, z plane is perpendicular to the molecular plane. So sigma y, z plane is perpendicular to the molecular plane. These two are shown in a single diagram here. Then the boron trifluoride, shape plane or triangular. This is plane or triangular. See, this is one plane, okay? This is one plane. This is one plane, and this plane will be, this is one molecular plane. Molecular plane is one. This will be perpendicular to what? The principal axis. So, is it horizontal or vertical? This is a horizontal plane. The molecular plane is, this is C3, and this plane is perpendicular to C3. So, this is a horizontal plane. This is a horizontal plane. So this is a horizontal plane. So here, this diagram is with reference to this orientation. Then this corresponds to this in the same plane. So the molecular plane is an XY plane. The Z axis is perpendicular to the plane of the molecule. The molecular plane is XY plane. It is perpendicular to the principal axis C3. So the molecular plane is sigma h. Then there are three vertical planes. One, this is one, then the two, and there's three. And each vertical plane passes through a boron atom and one of the fluorine atom. Now PtCl4, the 2 minus ion. There is one, this is the PtCl4 2 minus ion. Yeah. This is C4. This is C4. This is C4. So, the plane containing the molecule is the horizontal plane. Then, there are four vertical planes. Say, this is one vertical plane, this is a second vertical plane. Then, this is a third vertical plane, this is a fourth vertical plane. And the first two, this and this, are the real vertical planes, whereas this plane and this plane bisects the angle between two C2 axes. So these are dihedral planes. I will show it diagrammatically. This is the sigma principal axis. C4 is perpendicular to the plane of the molecule. Therefore, the plane of the molecule is sigma h. Then this corresponds to this and this. Then this diagram corresponds to this and this. Now, there are four planes, all perpendicular to the plane of the molecule and containing the C4 axis. So, all these four planes are vertical planes. These four vertical planes are not equivalent. They may be separated in two sets, each having two planes. In one set, each plane passes through the platinum atom and two diagonal. Each set passes the platinum atom to this. They are the sigma v. In the other set, the plane contains the platinum atom and bisects what? The chlorine, platinum, chlorine bond angle. In the other set, each plane passes through the platinum atom and bisects the chlorine-platinum-chlorine angle. These two planes bisect the angle between two C2 axes, and they are called the dihedral. So this is horizontal plane, these are the vertical plane, and these two are the dihedral plane. So the horizontal plane is perpendicular to the principal axis. A vertical plane contains the principal axis, and the dihedral plane bisects the angle between two C2 axes. Likewise, we can discuss 1 sigma H and 5 sigma V. Then benzene, there will be 1 sigma H, 3 sigma V, and the 3 sigma D. This is exactly similar to PTCl4, 2 minus ion. Now, the methane molecule. I think I have time to discuss this. See, this is one of the trickiest molecule to discuss it in the group theory, methane molecule. See, this is a tetrahedral methane molecule. Now, this is the perspective of methane. This is how you normally imagine the methane. Now, let me slightly hold it like this and diagrammatically represent this. Say this bond is this bond. This bond is pointed towards me. This is pointing away from me. These two are in the plane. So you represent it like this. Okay. This is a wedge bond which is pointed towards it. This is hash wedge bond which is pointed away. This is for this configuration. For this configuration, this is a diagram. Now, this bond is called the wedge bond pointed towards us. This is called the hashed wedge bond, the pointing away from us. The methane is one of those molecules whose symmetry elements, the symmetry operations, are not very easy to visualize even with the help of a molecular model. So even with the help of a molecular model, it's not very easy to visualize the symmetry elements and symmetry operations in the methane molecule. The principal axis is a C3 axis, okay? This is the C3 axis. This is a C3 axis. This is a C3 axis. And how many such, and the C3 axis passes through what? The hydrogen atom and the carbon and the center of the triangle formed by the 3 hydrogen. So this will be passing through the hydrogen, carbon at the center of that. That is C3 axis. Now, how many C3 axes will be there? Corresponding to each hydrogen, there will be a C3. So 1 C3, second C3, third C3, 4. There are 4 such axes. Now, I make a statement. The methane molecule has 6 vertical planes. Methane molecule has 6 vertical planes. Are you able to visualize these vertical planes? Is there anybody who can visualize the 6 vertical planes in the methane molecule? This is one of the toughest jobs. See, the convincing the students of the presence of the 6 vertical planes in methane molecule is always a challenge for any teacher. Say in a real classroom situation, I will be able to convince a student with the help of the model. But I cannot do it with the help of the model in a webinar. So I will use an alternate method to convince you of the presence of the 6 vertical planes. See, first, look at this. And this is a trick here. Instead of holding the molecule like this, I'm holding the molecule like this. This is another perspective of the methane molecule. This is another perspective of the molecule. These 2 bonds are pointing up. These 2 bonds are pointing down. So, diagrammatically, these are the wedge bonds. These are hashed wedge bonds. Now, I will show with the model first. I rotate this about this axis, passing through the carbon, and then if I rotate about this, what will happen? Through 180 degree. These 2 will be interchanged. Oh, so sorry, the plane, not rotation, there's a plane. You consider this plane or this plane containing these two. So this plane will contain what? The carbon and the two hydrogen. And this plane will bisect this hydrogen, carbon, hydrogen. Okay? So this plane will contain the two hydrogen and the carbon. 1, 2, 3. Imagine this. This will contain this, and this will, you will bring it here. This will bisect the hydrogen, carbon, hydrogen bond angle. This is the model. I will show it in the diagram. The two bonds are pointed towards us and two bonds are pointing away from us. Imagine a plane passing through the two horizontal hydrogen atoms and the carbon atom and bisecting the hydrogen, carbon, hydrogen bond angle. See these are the two horizontal and bisecting the hydrogen, carbon, hydrogen, the bond angle. Now, the carbon atom and the two horizontal atoms will lie in this plane, and the two hydrogen atoms, coded red, will be mirror images of each other. This plane, these two will be mirror images of each other. These three will lie in the same plane. So, this plane is a symmetric plane and it contains the C3 axis. So, this is one of the 6 vertical planes. So, one of the 6 vertical planes contains a carbon atom and the two hydrogen. We are identifying one such vertical plane. The remaining 5 vertical planes may be visualized as follows. If we label the 4 hydrogen atoms 1, 2, 3, and 4, the possible combinations of carbon and the two hydrogen atom will be as follows. Because this vertical plane contains a carbon and the two hydrogen. So I try the possible combinations of two hydrogen atom and the carbon. I start with the 1. Hydrogen 1, carbon and the hydrogen 2. Then hydrogen 1, carbon, hydrogen 3. Then hydrogen 1, carbon 3. So if this is 1, 2, 3, 4. Then 1 and 2, then 1 and 3, 1 and 4, like that. Then the hydrogen 2 and the 3. After exhausting 1, I come to 2 and 3. Then 2 and 4. Then finally 3 and 4. Then how many possibilities are there? There are 6 possibilities. Or there are 6 possible combinations and hence 6 vertical planes here. So each vertical plane will contain the carbon atom and the 2 hydrogen atom. There are 6 possible combinations of 2 hydrogen atom and the carbon. Hence, there will be 6 vertical planes. And now you can take a molecular model and try to visualize this. It's not that easy to show it in the small screen here. But I normally, show these 6 vertical planes to my students in the classroom. Then ammonia. Ammonia, there are 3 sigma V. See, this is a sigma V, this is a sigma V, this is a sigma V. There are 3 sigma V. Then ethylene. And of course, there are 3 mutually perpendicular planes. So I will just flip it. Say, look at this. Look at this. Ethylene has 1 sigma H and the 2 sigma V. This is a Z. So sigma H will be this XY. This is a sigma H plane. Then, and this is XZ plane. This molecular plane is XZ plane. Then there will be a third plane, which is sigma YZ is equal to. And to visualize, represent these planes, use those concepts I explained earlier. Then operation generated from the mirror plane. I will finish this also in this session. This will take hardly 5 or 10 minutes. Both the symmetry element and the symmetry operation are designated by the same symbol sigma. like the identity, the mirror plane, the sigma. The sigma stands for symmetry element as well as symmetry operation. A mirror plane can generate only two operations. The two operations generated by sigma are sigma and E. Now you recall, identity can generate only one operation. Sphere can generate n operation, whereas a mirror plane can generate only two operations, sigma and identity. If the reflection about the plane is carried out n times, it is denoted as sigma to the power n. Now look at this. This is sigma. You carry out the reflection once. This is sigma 2, then sigma to the power 3, sigma to the power 4. Now you compare, all these are symmetry operations. The hydrogen atoms label 1 and 2. Now this configuration is identical to which configuration? You just look at this.
Sigma 2.
Sigma to the power 2. We find that sigma to the power 2 is identity. Then you compare these two. That is the sigma, the configuration arising from the sigma, and the configuration arising from sigma to the power 3. Are they equivalent or identical? This configuration and this configuration, are they equivalent or identical?
Identical, sigma and sigma 3.
So, equal as sigma to the power 3 is equal to sigma. Then sigma to the power 4 is, you compare this and this, they are identical and so on. In general, sigma to the power n is sigma if n is odd. Sigma to the power n is identity if n is even. Sigma to the power n is sigma if n is odd. Sigma to the power n is equal identity if n is odd. E can generate only one operation. The Cn can generate n operation, and the sigma can generate two operations. And sigma Cn to the power n is identity whether n is odd or even. E to the power n is identity whether n is odd or even. But in the case of the mirror plane, if it is odd, sigma to the power n is sigma. If it is even, sigma to the power n is identity. Then inversion center or center of symmetry, this is easiest. This is how you define an inversion center. If a line drawn through a point in a molecule and extended in both directions encounters equal points in either direction, then the point through which the line is drawn is called an inversion center. So you draw a line, you will get this. This is trans dichlor, so this is an inversion center. Then both the symmetry element, symmetry operation are designated by the same symbol I. Like the mirror plane, the inversion center also can generate only one operation apart from identity. Or I can say that can generate only two operations, namely I and E. The effect of performing the inversion n times I to the power n. Inversion is actually a reflection about the point. So I to the power n is equal to E if n is even. The I to the power n is I if n is odd. Exactly similar to the mirror plane. So E to the power n is E. Cn to the power n is E whether n is odd or even. But sigma to the power n is sigma if n is odd. Sigma to the power n is E if n is even. The same is the case with the inversions. Then illustration. These are all simple molecule which you can very easily. This is what? Staggered ethane. So we just got an inversion center. Then PTCl4 2 minus AB4. PTCl2 NH3 twice. Trans. So trans AB2C2 planar. Then ethylene. These are some of the molecules, the inversion center. Then these are octahedral molecule AB6 or the example AB6 or AB4C2. Then benzene, this is the inversion center. Then naphthalene has the inversion center. Now, there are molecules which are symmetric about the central atom, but which do not possess an inversion center. Can you think of the molecules which are symmetric about the central atom, but which do not possess an inversion center? Can anyone tell me at least two molecules which are symmetric about the central atom, but which do not possess an inversion center?
H2O,
One
water.
an example of the molecule which is symmetric about the central atom. What about this? This is symmetric about the boron, but by the definition of the inversion center, if this molecule does not possess an inversion center, if it is there for there to be an inversion center, you must have the fluorine atom here. But the molecule, another example, the methane. The molecule is symmetrical about the carbon atom, but it doesn't possess an inversion center. So the next presentation will be the symmetry element, symmetry operation, the part 3, improper rotation axis. I think